Hello everyone, and welcome to today's webinar. Before we get started, I'd like to go over a few items. We've taken a screenshot of an example of the attendee interface. You should see something that looks like this on your own computer desktop in the upper right-hand corner. Most likely, by default, you're listening in using your computer's speaker system. If you would prefer to join over the phone, just select the telephone in the audio pane and the dial-in information will be displayed. For those of you viewing live, you will have the opportunity to submit questions via the chat box in the questions pane of the control panel. You may send in your questions at any time during the presentation, and we will address them during the Q&A session at the end. You might also find some helpful resources and information in the handouts section of your control panel. After today's presentation, we will make this recording available, so no need to panic taking notes. Just focus on the presentation and keep your eyes out for an email from us with the recording. At the close of the webinar, we ask that you complete the survey so that we can improve our webinars and identify how we can better serve you. And of course, be sure to stay tuned for our next webinar. Now, the moment you've been waiting for. Let's get started. Virtuosity is Bentley's e-commerce platform that provides an easy, affordable way to purchase practitioner licenses of Bentley software paired with expert services, training, and mentoring.
Hey everyone, good afternoon, good morning, good afternoon, and good evening. Welcome to our webinar and thank you for joining us today. So let's move on with our presentation. Sorry. So I'm Jamie. I'm the sales engineer for PLAXIS in Southeast Asia region. And with us today, we have Satadal, our user success manager, and he'll be sharing with us on our topic later. So today's agenda are on Bentley Geotechnical Engineering Solutions, Virtuosity Practitioner Licenses, demonstration of PLAXIS by Satadal, and then we'll move on to explain on how to get started and obtain pricing information for Virtuosity subscription. Lastly, we have the question and answer session. So Bentley Geotechnical Engineering Solution consists of two key areas. So on the right side is the Geotechnical Information Management Solution. It's used for subsurface data management and reporting. And on the left side here is our Geotechnical Analysis Solution. We have PLAXIS 2D, PLAXIS 3D, PLAXIS Monopile Designer, and PLAXIS LE. A more detailed explanation of these geotechnical analysis solutions will be shown in this next slide. So as mentioned just now, PLAXIS 2D and PLAXIS 3D, they are our finite element solutions. They are used for analysis of deformation and stability in soil and rock. So each of PLAXIS 2D and PLAXIS 3D consists of three main product tiers. The base tier, we call it just PLAXIS 2D or PLAXIS 3D. One tier higher, we have PLAXIS 2D or PLAXIS 3D Advanced. And the highest tier will be PLAXIS 2D Ultimate or PLAXIS 3D Ultimate. PLAXIS Monopile Designer is used for laterally loaded monopile design. And PLAXIS LE for limit equilibrium is for limit equilibrium slope stability analysis. So if you need a complete solution of a geotechnical engineering analysis solution, then you can go for the work suite. It is a combination of, for PLAXIS 2D, is combination of 2D Ultimate and 2D LE. 3D work suite is a combination of 3D Ultimate, 3D LE, and PLAXIS Designer. Our focus today will be on the finite element solution. So this is our a breakdown of the tiers of PLAXIS finite element. The lowest tier, PLAXIS 2D or PLAXIS 3D, it is for very basic function, like just for analysis for deformation and safety that does not require consideration of consolidation or any thermal flow, groundwater flow, creep, or time-dependent effects. And PLAXIS 2D or PLAXIS 3D Advanced is one tier higher. So this can be used for analysis with steady-state groundwater flow, consolidation analysis, creep, pseudostatic analysis, and degradation of soil due to cyclic loading. And also in PLAXIS 2D, it includes also the steady-state thermal flow analysis functions. And the highest tier is PLAXIS 2D or PLAXIS 3D Ultimate. This tier's capability is exactly the same as that of the version 20's PLAXIS 2D or PLAXIS 3D suite, which has all the additional modules included in it. So it includes features to analyze effects of vibration in soil, like earthquake or traffic load, or any time-dependent variation of groundwater level for simulation of hydrological conditions. And also in PLAXIS 2D Ultimate, there is also the features to analyze effects of time-dependent heat flow included. So, sorry, before we move further, we would like to post our first poll question. Kindly participate in this poll for us to understand all of you better. Right, we'll be closing the poll in 5, 4, 3, 2, 1. Thank you very much, everyone. So let's move on to the next session on Introduction to Virtuosity. So Virtuosity, we are a Bentley company. We focus on our e-commerce web store, www.virtuosity.com. So in Virtuosity, the software that we provide is a 12-month license. It comes with customizable trainings, mentoring, and expert opinion services. So here we'll explain to you how it works. When you purchase a software from Virtuosity, let's say if you purchase PLAXIS, it means that you're purchasing Virtuosity subscription. So with Virtuosity subscription, it includes the license itself and also keys or credits. With these keys, you can use them to redeem free trainings, expert services, consulting, or mentoring services. This is to ensure that you can get started immediately. And the number of keys, they vary based on the software that you purchase. So this is a general list of what you can use your keys for. All these are online trainings. So we have the virtual classroom training, on-demand sessions for you to learn at your own pace, standard training for you to understand the software and the basic workflow of the software, customized training, consulting, and mentoring to suit your team or your project specific requirements. So now we'll start our demo session. Please give us a moment.
Hello and welcome to this webinar on PLAXIS in mechanically stabilized walls, built-up slopes. My name is Shatadol and I'm a User Success Manager with Virtuosity, a Bentley company. Geogrids and soil reinforcements are an essential part of substructure construction, especially when we are dealing with soft soil with lesser cohesion. So we must make sure that the built-up slopes or the mechanically stabilized excavation retaining systems that are to be used in any project are safe throughout the construction and/or its own life cycle. This is why we use PLAXIS to model and analyze different geogrid systems. PLAXIS has the wonderful capability of analyzing a structure throughout various phases in its life cycle. That helps us isolate the weakest phases. This in turn helps us make our structure safer and more stable for the project. In this webinar, there will be 4 sections. First, we will understand about geogrids and how it's addressed in PLAXIS. Then we will see some demos of geogrids in PLAXIS 2D. This will help us get an overview of what we can do in PLAXIS. That is, in no means exhaustive. Then we will see what Virtuosity has in store for you and how you can get started with your Virtuoso subscription. And finally, I will try to answer some questions that you might have. Now let's start with our first section where we will understand about geogrids and how it's addressed in PLAXIS. In this section, we will check out the different geogrids first. Then we will see some features of geogrids in PLAXIS, then some interactive features of geogrids in PLAXIS, some features of interfaces for geogrids, how to address permeability for geogrids, output visualization options for geogrids that are available, and finally the different material properties that are available for geogrids. Geogrids are objects that are generally used to model soil reinforcements. This could be geotextile, geogrids, metal stiffness, etc. We can use this tool to model all kinds of soil reinforcements that we can think of. Some examples of the same can be seen in here. We can use geogrids to create a vertical excavation or a soil retention without a retaining wall as shown in the leftmost image. We can have built-up slopes as seen in the image in the center. We can also have embankments with geogrids as shown in the rightmost image. This is true especially when the embankment is made of soft soil. Geogrids are modeled with 3 or 5 node line elements depending on the soil elements. When 15 noded soil elements are used, the geogrids are defined by 5 noded line elements, and while 6 noded soil elements are used, the geogrids are defined by 3 noded line elements. Geogrids can be elastic or elastoplastic. There are other material types available with PLAXIS for geogrids, however, broadly, these are the two that are used. For elastoplastic, there is a maximum limit of axial tension that is to be supplied, crossing which the geogrid will enter its plastic deformation stage. Geogrids does not have any flexural rigidity. They can't carry moments. They only have axial stiffness. The axial stiffness only allows for tension. Geogrids cannot sustain compression. For geogrids, the updated mesh option is needed to capture the accurate soil behavior. Here are some properties and interactive features of geogrid elements in PLAXIS 2D. In a geometry model, geogrids without assigned material properties appear as light yellow lines, whereas geogrids with assigned properties appear in their material color. When creating geogrids, corresponding geometry lines are created simultaneously. This is just like any other structural elements like plates or interfaces or line loads. The material property of a geogrid is essentially an elastic normal or axial stiffness. This can be specified in the material database. Geogrids can be raised by selecting them in the geometry and pressing the delete key, just like any other elements in the PLAXIS model. Just like any other element, geogrids can be activated or deactivated in calculation phases using staged construction as loading input to consider or ignore respectively their effects in the calculation of that phase. The basic material parameter for geogrids is the axial stiffness, but in addition to that, the tensile strength can be limited to allow for a simulation of tensile failure. After a successful calculation is performed in the output program, the axial forces in a geogrid element can be viewed graphically or can be tabulated. When using geogrid elements in PLAXIS 2D for modeling of true geogrids, most applications require the use of updated mesh calculations. This is done to take the membrane effects into account. Most applications of geogrid elements also require use of anisotropic properties to avoid unrealistic shear deformations. Here is a quick look at the features of interfaces of geogrid elements. These interfaces allow accounting for the sudden change in material properties, for example, friction within the soil and friction between soil and the structure or geogrid. The interfaces are joint elements that are added to the geogrids. These allow for proper modeling of soil-structure interaction. Interfaces can be placed on either or both sides of a geometry line. Placing an interface on both sides enables a full interaction between structural objects, or in our case, geogrids, and the surrounding soil. To be able to distinguish between two possible interfaces along a geometry line, the interfaces are indicated by a plus sign and a minus sign. These merely represent the direction of the interface with respect to the structural element along the Cartesian axes. Here are a few notes regarding permeability of geogrids. By default, geogrids are permeable. Impermeability can be introduced by assigning an interface to the geometric entity. In principle, interface permeabilities like cross-permeability and parallel permeability are defined in the corresponding material dataset. However, note that for an interface, a checkbox is available in the Object Explorer to make an interface either active in flow or inactive in flow. In flow-only calculations, no structural element needs to be assigned to the geometric entity as deformations will not be taken into account. Hence, it's sufficient to use only interfaces to block the flow. Note that the endpoints of an interface are always permeable. Once the calculation is successfully finished in the input module, the results will be available in the output module. The following visualization plot types are available for geogrids. The deformed shape of geogrids is displayed. The relative deformation is indicated by arrows. Scaling of the results is possible. The distribution of results in geogrids is displayed. Scaling of these results are also possible. The wireframe distribution of results in geogrids or interfaces is displayed. Scaling of these results are also possible. The distribution of maximum and minimum values of the resulting forces in geogrids up to the current calculation step is displayed. Scaling of these results are also possible. The wireframe distribution of the maximum and the minimum values of the resulting forces in geogrids up to the current calculation step is displayed, and scaling of these results are also possible. Here are a few notes about the material properties of geogrids. As already mentioned earlier, geogrids can be isotropic, which means same stiffness in both directions, and anisotropic, which means different stiffnesses in the two directions. Geogrids have only axial stiffnesses in the in-plane and the out-of-plane directions. In case of isotropic geogrids, we only need to provide value of one of these, specifically EA1, which is the in-plane axial stiffness, as it's going to be same in both the directions. While for anisotropic geogrids, we would need to provide the value of both the in-plane and out-of-plane stiffnesses. The axial stiffness is usually provided by the geogrid manufacturer and can be determined from the diagrams in which the elongation of the geogrid is plotted against the applied force in a longitudinal direction. The axial stiffness is the ratio of the axial force, F, per unit width and the axial strain, i.e. delta L by L, where delta L is the elongation and L is the original length. Geogrids could be elastoplastic. As we have already mentioned earlier, we can provide a maximum force in the in-plane direction for the isotropic and both in in-plane and out-of-plane direction for the anisotropic geogrids. When the forces exceed this value in the geogrids, they enter their plastic deformation zone. Geogrids can behave in a nonlinear elastoplastic way. For that, a diagram for the axial force against the axial strain is required for each of the directions as applicable for isotropic or anisotropic behavior. PVC geotextile presents a creep behavior under sustained loading. To take account of that, PLAXIS has the provision to apply viscoelastic or time-dependent material properties to geogrids. This material model follows the Kelvin-Watt single-element representation as seen in here. The model uses two nonlinear springs. This model really captures the nonlinear behavior. Here we need to provide only one instantaneous value of the elastic stiffness and a stiffness obtained from a creep test. Here are the material parameters required for the viscoelastic behavior. Elastic stiffnesses in both the direction during initial strain increments, elastic stiffnesses in both the direction during long strain increments, maximum forces in both the directions, and the retardation time, which is the time where a linear extrapolation of the initial creep rate intersects the long-term displacement line. This is the section where we shall see some demonstrations of geogrids in PLAXIS. In this section, we will go through three extensive examples. The first one is a comparison of models of unreinforced and reinforced soil retaining structures. In the second example, we will analyze stability and consolidation on a geogrid reinforced retaining wall. The final example is about stability, consolidation, and dynamic analysis of a geogrid reinforced slope. Before we go ahead, I would like you to take a note of the fact that the examples shown in here are just typical ones. We can use the same concepts in more complex situations and everywhere else.
In the first demonstration, I will be doing a comparison. I will compare the results of this excavation with another one. In this file, the excavation is stabilized using a retaining wall, while in the other file, the excavation will be stabilized using geogrids. Let me show you the different phases in this project. Initially, I have a flat ground with water at the top. In the next phase, I have installed a retaining wall. From phase 2 through to phase 6, I have excavated the ground in 5 layers. In the final phase, I have performed the factor of safety calculation to check the stability of the construction. For the retaining wall, I have used a plate element with certain properties to make it behave like a retaining wall. Along with that, I have added interfaces to the wall on both the sides. These interfaces will help take account of the soil structure interaction between the retaining wall and the surrounding soil. Let me go back and show you the model properties of this model. Here we are using a plane strain 15-noded model. The x-min is 0 and the x-max is 200 meters. The y-min is 0 and the y-max is 100 meters. Now let me show you the model from the beginning. So I'll go to the Soil tab to start with. I double-click on the borehole to open up the Modify Soil Layers window. Here you can see that I've used only one soil layer going up to 100 meters deep. This is to keep the model as simple as possible just to see what the effects of this excavation imparts here. The water head is at the ground level. This, however, is not affecting the comparison that we are trying to see. Now let me show the soil material that I have used in here. One brilliant feature of PLAXIS is that you can store the material model that you create in a global repository in your computer. You can use these soil models from different files within the same computer. These materials are saved in a separate file. So that means you can easily share the materials with your colleagues. The soil model that I have used here is a Moore Coulomb model. I have used a drained type of soil. This is done to ignore the stresses due to the presence of the water table there. For the Moore Coulomb soil model, the parameters that are required are based on Moore Coulomb criteria. For example, I have here the stiffness properties like Young's modulus, Poisson's ratio, and the strength properties like cohesion, friction angle, and dilatancy angle. There are some alternative parameters as well as some other and advanced parameters here. You can apply appropriate values to these parameters to get a more accurate simulation and subsequent results for a structure. Here are the stiffness and strength properties that I've used for this model. I have used some arbitrary boilerplate values such that the soil does not collapse but nothing too drastic. This would not be of much importance to the comparison as I would be using the same material for the soil in the other model. In the groundwater tab, you can provide values for parameters pertaining to the groundwater flow within the soil. You could use a dataset to get the predefined values, or you can enter sieve analysis results in here. In this example, I'm performing a drained analysis, so I won't be requiring the groundwater parameters. The next tab is thermal. It can be ignored for this example. Next, the interfaces. For this example, I have used a rigid interface, so there is essentially no strength reduction in the interfaces. However, while using geogrids, you would need to change the strength to manual and change the R interfactor to something less than 1, preferably 0.5, to account for the strength reduction. And finally, the initial tab. Here you can provide the K0 determination method. For this example, it's automatic. So the initial stresses in the initial phase would be calculated automatically. You can change this to manual to apply different values for the K0s. Next, as you can see, I can select different types of materials and create different material datasets for each of them as and when required. If I select plate, you can see that I have also created a material for the retaining wall. Let me open this up to show you the details of the material. Here, I would like you to note that I am using a higher stiffness for the retaining wall. Once that is done, I will go to the Structures tab. It is in this tab that you generally add the structures like retaining walls, anchors, geogrids, etc., and different lines and loads. If you have an unconventional soil layer, you can also add that in the Structures tab. For the retaining wall, I have used a plate, and a plate can be placed from under the Create Line tool. I have also placed a few lines to divide the soil in different sections or soil masses. I have done this so that I am able to select the soil bodies and activate or deactivate them as required in the Staged Construction tab. Then I would go to the Mesh tab and create the mesh for this model. Since the calculation is already done, I am not going to remesh the model. Then I would need to go to the Flow Conditions tab. However, this example doesn't consider the effects of groundwater, so I can directly go to the Staged Construction tab. I have already discussed regarding how the construction phases are designed in here. Since the calculation is already done, I can readily click the View Calculation Results button to check the results of this calculation. As you might already know, the default view shows the scaled up deformed mesh. Now if I go to the total displacements, you can see the failure mechanism somewhat in here. To better see the failure mechanism, I can try some other plots. However, the best one in this case would be the incremental deviatoric strains. Here you can see the active and passive failure mechanisms clearly. This should also dictate the length of the geogrids that must be used here, for example up to the 55 or 60 meters mark from the face of the excavation. To better understand the stability of the construction, I have already created a factor of safety chart from the factor of safety phase that I had created and calculated from and after the last excavation phase. Here you can see that the factor of safety after the final excavation comes out to be 1.4. This means the construction is safe even for conditions which are 1.4 times as worse as the current situation. Now moving to the model with geogrids. Here you can see that I have used the same excavation with a relatively small retaining wall and I have some geogrids. These are smaller than what I had predicted that this model needed from the previous calculation results. I have placed one for each of the excavation levels. In this example, you can see that the stiffness of the wall is negligible here. I've used the wall just as a facial covering in front of the reinforcement. The geogrids are the ones that are taking the loads in here. Here you can see the properties of the geogrid that I have used in this example. I have used an isotropic geogrid model, so you can expect some unrealistic shear deformations in the results. However, in this example, I am more concerned about the factor of safety, or in other words, the stability of the model. You can see that the phases are similar to what I had in the previous example. However, in each excavation stages, I have activated the geogrid that's in that depth. Now, since I had already performed the calculations, I can readily click on the View Calculation Results button to view the results in the Output module. As usual, the default output is of the deformed mesh. Now, in the incremental deviatoric strain plot, you can see the geogrids have arrested the failure mechanism somewhat. This is even though I haven't used geogrids as long as what I had determined from the previous calculation. Now, in the factor of safety chart, you can see that the factor of safety obtained from here is a little above 1.5. This means that this model is now more stable than the last example. This model can be further optimized with more layers or longer geogrids. For the geogrid, the output also gives me view of the various forces that are working within them. This is the view of the actual forces working within the geogrids. I can modify the scale a little bit to make the individual curves a bit more visible. If required, I can open a tabular form of the results like so. Now, let me open another file with longer geogrids but of the same count. In this file, everything else is exactly the same. I have run the calculation already, so let me open the output directly. Here you can see that the soil mass moves as a whole block. This is because of the presence of the geogrids. Now in the incremental deviatoric strains plot, you can see that this distribution of the geogrids arrests the failure mechanism very efficiently. Let me open the axial forces view of the geogrids. I can change the scale to make the curves visible properly. Here you can clearly see that the failure has been arrested and the tension has been taken up by the geogrids. Finally, let me show you the factor of safety that is obtained in this construction after the final excavation. As you can see in this curve, the factor of safety is more than 3. This is more than double than the first example with only the retaining wall and also the second example with shorter geogrids. The takeaway from these 3 examples is very beautiful. You can use PLAXIS to get an idea regarding the specification for geogrids required. The more you iterate, the more you can optimize the model. This can really help you get a good mix of safety and cost efficiency for your project. In this demonstration, I'm going to perform a similar comparison as the last one. However, in this case, I would be adding a building load to be applied at the very beginning of the construction. Along with that, I would also account for the consolidation after each excavation phase. Now, if I go through the different phases here, you can see that they are exactly the same as the first model in the previous example. However, the only difference here would be the presence of the consolidation phase after each excavation phase. Now, if I select the load, you can see in the Selection Explorer, the load here is 30 kilonewtons per meter per meter. Due to the presence of this load after each excavation, the pore pressure increases right under the load. So when I allow for consolidation in a phase right after an excavation phase, the pore pressure dissipates. This would create a significant change in the results than what you have seen in the previous example. Now let me show you the details of an excavation phase. You can see that this is a simple plastic calculation. But the details of a consolidation phase is very much different. The calculation type for this phase is consolidation. The loading type is minimum excess pore pressure. This type of loading would require a value of pore pressure where the calculation would stop the consolidation phase. This automatically calculates the time required for the consolidation. The next excavation is done after the consolidation of the previous excavation achieves the supplied minimum excess pore pressure. Now let me show you the changes that are required in the soil to account for the consolidation. The very first thing that you may notice is that I'm using undrained conditions to account for the stiffness due to the presence of the water table. The other parameters are exactly the same except for the Poisson's ratio. I've increased it to 0.4. I have already finished the calculation, so I can directly go to the output module to see the results of the calculation. As usual, the output module opens up in the deformed mesh view. Now if I go to the last consolidation phase, the maximum value of deformation can be seen to be 0.54 meters. In the incremental deviatoric strain plot view and the factor of safety phase, you can see the failure mechanism. The factor of safety chart shows the factor of safety for this construction. The factor comes out to be somewhat near 1.09. This range of factor of safety is not good. This construction seriously requires some strengthening. Now, as you might be able to guess already, I have created an exact same model, this time with the longer geogrids as was shown in the last model of the last demonstration. Here I start with the initial phase, then I have the phase where I turn on the building loads. In the next phase, I install the wall, and then I start with the excavation and installation of geogrids. In the case of the phases for the excavation layers, you can see that I have turned on the updated mesh option. In the case of the consolidation phases, I have used the minimum excess pore pressure for the loading type. This is exactly the same as what I had done in the previous model. In the final phase, as you can see, I have performed a factor of safety calculation. Since I have already finished the calculation, I can now directly go to the output module by clicking on the View Calculation Results button to check the results of the calculation. The output window opens up with the deformed mesh as usual. Now, if I go to the incremental deviatoric strain, you can see that the failure is again arrested by the presence of the geogrids. The factor of safety chart for this model shows the factor of safety for this model is close to 2.45. This is again more than double the previous one. Now, from here, I can perform more iterations with different designs of the geogrids, i.e. depth, number of layers, etc. to find an optimum solution for a safe construction. Apart from this, since the model includes some consolidation analyses, you can check the vertical displacements, or in other words, the settlement of the model. As you can see here, the maximum settlement after the final consolidation stage is around 33 millimeters. The settlement occurs near the fringes of the geogrids. This model also shows a fair amount of heave at the center of the excavation. This is due to the effects of consolidation and the presence of the load. More Coulomb soil models generally present a higher amount of heave. For this reason, a more accurate simulation of the real-life scenarios can be presented by the hardening soil or the HS small soil models. I'll be using the hardening soil model in the next example, so you can see some details regarding that there. This concludes this example. The point I would like to make here is that you can use geogrids instead of retaining structures to make the construction cheaper. Along with that, you can use PLAXIS to optimize that structure better for safety and cost efficiency. This is the last demonstration. In this demonstration, I'm going to show you this embankment. As you can see, this is the original condition of the site. I've imported the data and regenerated the surface. In the phase 1, I've excavated the left part as you can see in here. You can see that volume there in the initial phase. I've excavated that in the phase 1. This is done so that I can construct the geogrids in that region on the next phase. So here in the phase 2, you can see that I've rebuilt one layer of the embankment with 2 geogrids at this region. In phase 3, I have added another layer of embankment with geogrids. In the phase 4, I have added another layer of embankment with geogrids, and then in the next phase, I allow for consolidation to happen before moving further. The reason I did that is I have anticipated that after building up to this level, I might have enough pore pressure buildup that I would need to dissipate. It is not absolutely necessary to have a consolidation phase at this stage of the construction. It is an engineering judgment. Now moving on, I have the next phase where I add another layer of embankments with geogrids. I have added 2 more phases with 2 more levels of embankments along with the geogrids. Again, after these 3 phases of embankment construction, I have added another consolidation phase to dissipate the pore pressure that might have accumulated after the first consolidation phase. After the consolidation is complete, I have activated the load in the final phase. This phase denotes the beginning of the service of the embankment. One thing to note here is the blue boundary lines that you can see at the sides and the top of the embankment. The blue line to the side of the embankment is a non-load bearing facing element, and the blue line at the top of the embankment serves the purpose of a mat that spreads out the loading throughout the surface of the embankment. This is to avoid any punching shear failure that might arise due to the heavy loading over the embankment. Now, with the model and the construction phases ready, I have added some safety checks. These safety checks would give me an idea about how the model behaves at different phases of construction and how stable those phases would be. It is again not an absolute necessity to have safety checks after every phase. It depends on your engineering judgment to pluck out the most unstable stages and perform a safety check for those ones. In this example, I've performed the first safety check right after the construction of the first embankment level. The next safety check is performed right before I have allowed for consolidation to happen. The third safety check is performed after all the embankment levels are added. This is just before I allow for the final consolidation to happen. The fourth and final safety check is performed after the construction is complete and the service period of the embankment has started, or in other words, after the application of the load. I've already performed the calculation for this model, so I can directly go and check the results here. But before that, let me give you a recap of what we have done in here, starting from the Soil tab. Here you can see that I have created only the 2 base layers using the borehole tool. There are the borehole layers, and the phreatic head is at 9.7 meters, which is at the depth of 300 millimeters from the top of this set of soil layers. Then in the Structures tab, I have imported the data for the surface and then regenerated the surface from here. How that can be done could be a topic for another webinar. Along with that, I have also added the layers of the embankment and the geogrids in here. Finally, I've added the plates to denote the facing wall of the embankment and the top mat, and added a line load on that mat. After this step, I went to the Mesh tab to create the mesh for this model. I have not changed anything in the Flow Conditions tab. I have the global water level from the borehole tool. And finally, the Staged Construction tab, which I have already shown you all the construction phases that I had considered for this calculation. Now let me show you the materials that I have used in here. For the soil, I have used 2 materials, one denoting sand and one denoting silt. For both the cases, I have used the hardening soil model with undrained drainage type.
to consider the stiffness from the water content. For the plates, I have used only one material. As you can see here, the plate has a fair amount of stiffness in order to dissipate the line load onto the embankment. And finally, for the geogrids, I have only one material. As you can see here, I have used somewhat realistic stiffness parameters to see the proper behavior. With that, let's go to the output module and see the results. The output opens up with the deformed mesh, and the maximum deformation here is about 79 meters. This is due to the fact that the deformation is calculated in a safety check phase. The safety calculation works in this way. So to see the proper results, I would need to see the results of the phase 10, which is the last phase. But before that, let me turn off the line load and then go to the incremental deviatoric strain plots to check the failure mechanisms. So you can see that the failure will occur at this weak soil layer. Now let's check the same thing for the phase 10, which is the last construction phase. Here you can see that there is another pattern of global failure. This failure mechanism barely touches the geogrids. A plausible way of going forward could be to expand the lengths of the geogrids in the next iteration. However, there are other parameters that you would need to consider before committing to such a decision based only on this plot. Now, to check other significant results of the construction, the next result that I would check would be the settlement after the final phase. The settlement happening here after the final phase is around 2.6 meters at this region. Now let me show you the settlement before the second consolidation phase. As you can see here, it's around 1.5 meters. Right after the consolidation, the settlement is 1.85 meters, a difference of around 35 centimeters. This settlement is attributed to consolidation only. So the point I'm trying to make here is that the consolidation phases are important to consider at key phases during your project. Now after the load is applied, the settlement increases to about 2.6 meters, which is again an increase of about 75 centimeters. So with the point that I just made about consolidation in mind, we all can agree that this model might need another consolidation phase after the loading is applied. That will be correct. However, this model right now is not wrong. You can approach a model in many ways. There are more than one ways to cook an egg. It's totally at your discretion how you would like to approach the model. Another beautiful feature of PLAXIS is the fact that you can see the results along a section if required. This section is a 2D plane as you would expect in a 3D model and a 1D line in a 2D model. So in this case, the section would be a line. So I can draw a vertical line here and check the settlements along the line in this model. Arranging the two views side by side could give you a better idea about the location of the section plane or the section line. In this arrangement, by pressing Ctrl and plus or Ctrl and minus, I can move the section line around and see how the vertical deformation, which is essentially the settlement, is changing. As always, you can obviously check the forces working in the geogrids. Right now it's showing the deformations, however it's only showing the vertical deformations. This is because I was in the settlements plot. Now if I change the deformations to total deformations, you can see that it shows the deformations in both the vertical and the horizontal directions. You can check the tensile forces like so. Right now the plot is scaled up and overlapping each other. To make it clearer, I can decrease the scale value. From here, you can easily get an idea of the loading that is happening in the geogrids. For example, the ones at the bottom are loaded at the toe. As you move up, you can see the loading is shifting towards the right. So this follows the global failure mechanism of the structure. This also drives home the point that the failure is being successfully arrested by the geogrids. You can, obviously, tabulate the loads if required. For example, you might need to check whether the loads are crossing a certain limit. However, this table right now shows that these geogrids can take much more loading than what's been applied right now. Back in the plot, you can see that the maximum tensile force is 245.6 kilonewtons per meter after the load has been applied in this structure. This could be another point which might direct an engineer for the next iteration with lesser number of geogrid layers, reduced length, or both in order to reduce the cost. This could be one of the discerning factors that can aid your engineering judgment to make your project safer and more cost-effective. Now let me show you some charts that I have created for this model. First, a chart showing the safety factors for the 4 safety check phases. You can easily see that the curves had not reached a flat line yet, but still, 2 of them crosses 5, 1 crosses 9, and 1 crosses 10. There are 2 big takeaways from this. The first one is that I don't need to increase the number of steps for the safety calculations, as increasing that increases the time required to finish the calculation. The second one is that the model is super safe even though the curves had not flattened yet. This means that I can now optimize the model for more cost efficiency. This is another discerning factor that can help engineers like you to make your project safer and more cost effective. The next chart that I would like to show is for consolidation. It plots excess pore pressure against time. At the beginning, after the construction of the first few layers of the embankment, the pore pressure rose up to 135.75. Then I allowed for the consolidation to happen. It took around 3 days, as you can see over here, to dissipate the excess pore pressure. Then, after the construction was complete, the pore pressure built up significantly once again. After allowing for consolidation, the pore pressure dissipated once again. This concludes the static part of this example. Now I would like to jump to the dynamic part of the same exact embankment. So here you can immediately recognize that this is the exact same model. There are only two major differences. The first is that there are no safety check phases, and the second is the new phase for the earthquake analysis. There are a few other changes in the model, and you can see them if you look closely. These are required for the dynamic loading, and I will explain them gradually. Let's start from the boundaries. I have used free field boundaries for the left and the right edges of the model. This simply propagates the wave outwards without any reverberation, which could affect the results of our calculation. In real life, there shouldn't be any reverberation coming from those regions. The bottom boundary, however, has a compliant base along with a free field boundary. Before I go any further into compliant base, let me explain the phase for dynamic analysis. The difference of this phase from any other phase is that the calculation type is dynamic. Along with that, there is a field for dynamic time interval. This is the time interval for which the dynamic signal will be applied to the model. In this case, the dynamic loading will be applied for 20 seconds. Now, I have mentioned dynamic loading and dynamic signal without explaining what that is and how it is applied to the model. To do this, I will now go back to the compliant base. Now, if I select the base, you can see in the Selection Explorer that there are different parameters related to dynamic analysis. You can note that I have used a multiplier for x direction. This multiplier is actually a dynamic multiplier for displacement of that boundary. Now, if I give it a value that varies with time, then there will be a time-dependent displacement of this boundary. Now, if the signal is at par with an earthquake, then I'll be successfully simulating an earthquake in that region. So, let me show you the signal that I've used for that multiplier. I've used a simple table of time versus multiplier to generate a signal and applied it to the compliant base. This signal is considered for the first 20 seconds of our calculation as per specifications provided in the dynamic phase. A few other things that I would like to mention here are interfaces. As you can see that I have used some interfaces at the left and the right edges of the model. This is to help us work with the free field boundary conditions. I will not go deeper into this. One other point would be the free field boundary conditions. That is applied from the Model Explorer window. Under Model Conditions and then Dynamic, you can see that the boundary conditions are available there. You can modify the boundary conditions of the whole model from here. Finally, in the earthquake analysis phase, you can see that there is an error. That is due to the fact that I have stopped the analysis midway. Dynamic analyses take time to finish. In this case, I should be able to see the results of the part of the dynamic analysis that was completed before I stopped the calculation. Now it's time to see the results of the calculation of this model. As usual, the output module opens up with the deformed mesh plot. The maximum deformation here is about 3.5 meters. This is after the earthquake analysis phase. A few steps of the earthquake analysis was finished before I cancelled the operation. So here you can see the steps. Steps and phases can be toggled from here. This concludes this demonstration and this presentation as well. I hope this was informative for you. Now, I would like to hand the stage over to Jamie to continue from here.
Thank you very much, Satadal. Thank you everyone as well for your attention. So we'll move on to the next session before the Q&A. We have our second poll question. Would appreciate your help to answer this poll question for us. Give me a moment. We would also like to inform that towards the end of the presentation, do take a few minutes of your time to give us some feedback on the next topic on this presentation or for future improvement as well. Thank you. Right. The poll will be closed in 5, 4, 3, 2, 1. Thank you, everyone. So we move on to the next session, just a quick run through on Virtuosity subscription. So Virtuosity is a 12-month subscription program. It has name, user, license. The user can be reassigned. This yearly subscription program, it does not have any additional maintenance component to be paid. So you will get full access to the software that you purchase. And with this, you have full control over your software cost. You'll have also access to technical support assistance, to software updates, and also expert services using the keys or the credits that come with your purchase. To use Virtuosity subscription, this is you just need to visit our virtuosity.com website. I'll now switch to the website just for a quick run through. So this is our website. If you would like to look for sort it by industry, the products by industry, you can look in here. Geotechnical engineering can be seen here. If not, you can also go to this product tab up here on the top left, geotechnical engineering, and these are the individual products that we have. If you would like to view all of them, you just need to click on here, and then it will lead you to this page. So here you can see PLAXIS 2D, PLAXIS 3D, 2D, monopile, PLAXIS Designer, LE, KINS, and Open Ground application. So if we go into one example, let's say PLAXIS 2D, you just need to click on View Details, and it will lead you to this page here. So the pricing of the product can be seen here. Once you load this page, it can be seen, here. This drop-down list shows you the different tiers of the PLAXIS product, and the currency varies depending on your country and your region. So moving down, then here we have the summary write-up of every different tier of PLAXIS, the technical capabilities explanation, product matrix for comparison of the features and function of the different tiers. So in different category. And then we have also some frequently asked questions and also the system requirements for you to check with your PC in your office or at home. So if there's any of product of your interest, you just need to select it and then add it to cart. Then you'll be able to see one number at your cart here. Go to the cart and follow the instructions to check out, and the software will be delivered to you upon payment. So for the number of keys, here it is. If you click on this item, how many keys are included? So you can see here, these are the number of keys that come with the purchase of every product. So PLAXIS 2D, the lowest tier, it comes with 3 keys. 2D Advanced, 2D Ultimate, and 2D Worksuite, it comes with 5 keys. For PLAXIS 3D, all PLAXIS 3D come with 10 keys. Other than that, if you go to this training, Virtuosity subscription keys, it will lead you to this page. Do take a look at this video. It will explain to you what you can use your keys for. And if you go to resources webinar, it will lead you to this page. So this is the categories of webinar that we have: structural analysis, offshore analysis, geotechnical engineering is here at the center. So under geotechnical engineering, you'll be able to see this list of our earlier webinars. These with the date, future dates, these are our upcoming webinars. So please feel free to join us. And also under the resources blog category, it will lead to our blog page. Geotechnical, you can also view those topics under geotechnical engineering at this link here at the top right, and it will lead you to this page. These are all our geotechnical engineering blog articles. And if you have any further questions or any further inquiries, not to worry, you can always reach out here at our chat box at the bottom right of our Virtuosity website. Then you can select the category of your interest. Our colleague will be in touch with you and will link you up with the relevant person in charge. Okay, then moving back to our presentation. So that's the short run through of our Virtuosity website. And we'll move on to the next, our upcoming webinar. So we have one under geotechnical engineering on 11th of November next week on working with rock mass anisotropy from a tunneling perspective. We also have another one under the offshore webinar category where we will show the interoperation between SACS and PLAXIS 3D, finite element for modeling of foundation elements. So please feel free to register and join us in these 2 events next week. Then we will move to our question and answer session. So in Q&A, let us take a look at the question. The first question that we would like to answer is a non-technical one. Person asked if there is any recording of this webinar. So the answer is yes, we will upload the recording of this webinar, but do allow us like a few days to process the file and upload it to our webinar website again. After that, you can just click on the link at our webinar page, and you can watch it at your own pace as many times as you want. Thank you. And moving on to the technical questions, I'll hand over to Satadal. Satadal, over to you.
Thanks, Jamie. Thank you. So we'll now move on to the Q&A for technical part. So the first question that I see here is which interface settings do you recommend? Okay, so the interface settings, actually, if you are to use separate set of materials for the interfaces themselves, then it will be better to follow what you have for the soil. Generally, what you do with the interface is you reduce the strength of the interface. Near the interface, there will be a strength reduction for the soil, and then it will then capture the soil structure interaction. So you can use the model that you have used for the soil because you have that depth of details about the soil. So you can, if you don't have much more details, you can't. For example, if you have an MC soil, if you're using a more Coulomb soil, and then you want to use H's for the interface, you don't have the parameters that you would like to use for the H's, right? For example, the triaxial loading and all the stuff. So for that kind of case, you would have to use the MC. And then if you are using H's already, then it's if you try to use MC for the interface, then you are reaching out for a simulation which is not as accurate as a simulation that you would have had if you had used H's, right? So it's generally recommended to use the same model that you have used for the soil. Okay. Now, let's go to the next question. What happens in the calculation when the ultimate tensile strength of the geogrid is reached? So if that is the case there, then you will actually get a large amount of deformation, which will stop the calculation, and it will say that soil mass seems to collapse. So you will see a large amount of deformation in that region of the soil. You can see the failure plane from the output when you get the error. Generally, when you have any kind of error in the calculation just stops. If there is a failure, the calculation will stop. So if the calculation stops, you will see that which phase has failed. Then if you open the fail, you'll see the kind of error that you're getting. The error, if the failure is like so, the error will say that soil mass has collapsed. Then you can open that phase in output to see what kind of collapse you have faced. If it's in the region of the geogrid, then it's probably the geogrid that has failed. Okay. So now the next question is, what happens when you have a slip plane, the properties of the facing? Okay, so yeah, I believe this is connected. The next question is also connected. How to model a wraparound facing correctly? Instead of using geogrid, we'll need to use geogrid material as facing. Right, so to wrap around, you can use geogrid materials. You can use plates, right, for the facing. You can use any of the materials that are there. But if you have a kind of factor of safety which has been affected by that kind of material that you've used over there, or if you get a premature deformation failure, right? So what you can do is you can use strengthening at those regions. This will mean if you get a failure over there, this will mean that if you do that exactly in real life scenarios, you might get a failure. Okay, so which is why you'd need to strengthen that region. Now, for strengthening in PLAXIS would mean that you'd have to strengthen that region in real life scenarios as well. You can use secondary geogrids over there. You can use more number of layers. You can use some angular reinforcements at those regions. So there are different kinds of ways to reinforce those regions specifically. So you'll have to consider those kind of reinforcements in this region, and you'll have to use, if you're using a single plate, you can't really model into that details for these regions, then you'll have to use a single plate, for example, if you're using plate, and then use the strength of the plate in such a way that it kind of simulates the scenario which is there in the real life case. So basically what PLAXIS is doing is it's simulating the real life scenarios for the geogrids and for the slopes. Okay. So the next question, there are a few questions here regarding, I have seen earlier, updated mesh. Okay, so updated mesh is used generally in those cases where there is a deformation, but the nodes have not changed their locations, right? So this could be during consolidation. This could be during safety factor analysis. Okay, so what happens is, for example, if I consider the case of safety factor analysis, you get large amount of deformations, but those deformations are just fictitious deformations. Those are caused to reach to the failure point, and then understand what factor of strength decrement caused that failure. So then that factor is reported. So in those kind of cases, you would use the updated mesh. If you take a close look, you'll see that the updated mesh is used on the phases which are right after the consolidation or right before the safety factor analysis. Okay, so there is another question for the non-load bearing facing. Okay, in that example, the non-load bearing facing was using the same material that was there for the mat, the top mat. That was because to keep the model simple as possible, but doing that might have accounted for some forces in the some kind of strength in the edges, but you can have different materials and you can see the exact same thing happening over there. So if you use PLAXIS already, you can just go ahead and try it out, because you'll be receiving the recording soon. So so if you receive the recording, then you can play and pause at your own discretion. So you can use this recording, and I have pretty much given at least a glimpse of all the materials that I've used. You can try creating those materials. You can try this out yourself and see what happens. And those of you who are not using PLAXIS, you can get in touch with us if you want to try this out by yourself. We can arrange for some kind of some way for you to check this out. Okay. Now let's go to the next question. So again, updated mesh, that has been answered. Interface between soil and geogrid, that is also answered. Any recording? Yes, recording will be available. How much for the Virtuosity subscription? Well, I believe this will be better answered by Jamie. Jamie, would you like to go ahead? Okay, let me see if there are any technical questions. Then I'll, if there isn't any, I'll hand it over to Jamie back again for this question. Okay, any difference implication by modeling interfaces for geogrids? Yes, there will be a difference because if you don't use interfaces, there won't be any depth, the drop in the strength over there. So there, in real life cases, there will be a drop in the strength. Well, if you use interfaces which are rigid interfaces, in those kind of cases you won't see any drop in the strength, because the R inter factor will be fixed to 1. So in those kind of cases you can go to manual and then reduce the strength, because in real life there will be a reduction in strength at the exact contact point between the soil and the geogrid, right? But the block as a whole will have more tensile strength. Now, going to the next one, how to calculate the EA for geogrid. Can we adopt 5% of the characteristic initial strength and 5% strain of the product technical data sheet? Okay, so this actually, the EA was given over there. There is an equation, which is the force that you get, and force per unit per meter actually, right? And then that is divided by the strain that you get. So 5% of the characteristic initial, that actually depends. So if you try to, well, this gives me an idea that, well, if you are trying to go for ULS, you can do that as well, right? So if you try to do for ULS, there is an option for doing ULS. There was another webinar done just before this one. there was an example of ULS there. You can go ahead and check over there. That was regarding uh, probably consolidation factors. Anyway, so you can go over there and check the scenarios. The fact is, you can use design considerations, and then from there you can use ULS in PLAXIS as well. Now, when will fully coupled flow deformation analysis will be critical? Okay, so fully coupled flow deformation analysis is required in the cases where you need to calculate for both deformation and consolidation in single phases. You have multiple phases, and to keep the model, to consider one in the other, you would need to use fully coupled flow deformation analysis. In our cases, you can see that we have used plastic analysis and then consolidation analysis. That kind of affects each other. However, the fully coupled flow deformation analysis will be, considering both the deformation from the plastic analysis and the consolidation and the settlement due to the consolidation, and it will affect each other in the same phase, right? So if you want more accurate results for the consideration of consideration of both the plastic and the consolidation settlements, in those kind of cases, you should go for fully coupled flow deformation analysis. Then we have another question: does geogrid modeling require large deformation to work in PLAXIS? Because I tried using for small deformation, and it seems like geogrid did not contribute much in the terms of action. Okay, in those cases, you'd have to use HS small models to consider the small strains, right? If you don't use the HS small model, it will not consider the small strains. It will ignore the small strains. So in order to consider the small strains, you'll have to use HS small model. Other than that, it accounts for both kind of strains. It can be small deformations, it can be larger deformations. The next question is, if the axial force of geogrid does not exceed the tensile strength of geogrid product, does that mean we can go for lower tensile strength geogrid in the material? Well, this is totally at your discretion. Well, the question is, if the actual force of the geogrid does not exceed the tensile strength of the geogrid product, can we go for a lower strength geogrid to probably to save some cost? That's totally at your discretion. The idea here is, in the whole presentation, you can see that what I was effectively mentioning, that there were a few amount of considerations that you have to take into account. For example, the first one being the safety, right? First one being the factor of safety, then the amount of deformations that you are getting in normal cases, right? So these are the few things that you can consider. Then how much of the load is being arrested, then the amount of forces within the geogrids themselves. So if you see that that is happening, that all the factors are pointing that you can go for a lower tensile strength, then obviously go for that. But I would like to, if I were you, I would do another iteration just to see if my factor of safety is somewhere between 1.5 to 2. But that totally depends on your considerations. You being an engineer, that's totally your decision. So you can go ahead and try that. But you have to keep in mind that there are a few factors that you need to consider. It's not just only one consideration. If all of them points to the fact that you can minimize the strength, you can just go ahead and minimize the strength, and that will really minimize the cost as well. So the idea here is, again, to optimize the model for cost and safety. Right, so we are at the end of the technical questions. So now the non-technical question about the pricing.
All right.
Where was the question? Yes, Jamie, yeah, please.
Okay, I think there's another question that just came in, the last one, technical one. Which cases is used for behavior of geogrid? Can you see that?
Yeah, I can. Yeah,
Mm.
I just got the question. Which cases is used for behavior of geogrid as plastic or elastoplastic? It totally depends on your consideration. It's not like plastic or elastoplastic. The two types of geogrids that we have is elastic and elastoplastic. So one is only in the elastic region, and the other one is using considering the plastic model as well. So
these two are available. Along with that, there are other options also available there. So if you go for isotropic and non-isotropic, so you can have, if you are using isotropic plastic, then you have only one force to use, isotropic elastic, sorry. And then when you use isotropic elastoplastic, then you have the plastic capacity. You have to mention the elastic capacity actually. And then when you have non-isotropic models, in those cases you have to apply the same for both the in-plane and out-of-plane forces. So, well, there is a continuous flow of technical questions, as I can see here. So the next one is it necessary to model compaction in layers to take account of the history of load on the soil? Not exactly. So to take the history on the soil, you can use the pre-overburden pressures. You can use those kind of stuff over there that is available. But you can model both kind of scenarios is okay to consider. So it's totally up to you what you can, what you would like to do, right? So you can apply it in the material itself, or you can create a building and consider it as the phase right next to the initial phase to create a load on the soil. Next one, and also since you said history, if you want to use compaction, and if you want to account for the compaction, the settlement, you can use consolidations after the first phase of loading, and for that you can use number of days. That's another way. Just there are lots of ways to approach a model, as I've just said in my presentation. So yeah, you can use any of the ways which predicts or which affects the soil similarly. Now a continuation from previous question: where does the reduction factor being used to calculate the long-term strength as geogrid per BS 2006 being considered in the? Okay, so for the long term, this is done for the long term. The creep and is considered in GeoGrid. I can't really say whether it's BS 8006, but the fact that I can really say here is there is no specification that is used in PLAXIS, but you can use your own specification that you can in PLAXIS, right? There is a way to consider creep, but that requires a longer session. But you can really consider creep in due to long-term loading. So that happens. There was one small slide, I believe, that I have talked about this one, in which I've really talked about this one. There is an option where we have used one model. Yes, yeah, Kelvin Watt's single element representation. That's the one that we have used in PLAXIS. So that is the time dependent viscoelastic calculation that that you can use in PLAXIS. However, there isn't any consideration of any standards. You can use your own standards if that's what you're asking. All right, so I think that's the end of the questions. Jamie, you can go ahead now.
Thank you very much, Satadal, and thank you everyone for your questions and your time. So for pricing of PLAXIS, as we have shown just now, you can actually view them in our website, Virtuosity website. And not to worry, you can either reach out to us, or at the end of this webinar, you can there is a survey question. Do mark the icon on wanting us to contact you back, and we will be in touch with you to discuss further. So yeah, we move on to our next session. If you need to be in touch with us, these are our contact details. Southeast Asia, you have that's me, Jamie. That's my email and phone number. India and Asia South, we have Siddhartha and Amal, and Australia and New Zealand, we have Kyle. So do contact us, or if you need further help, as mentioned just now, there is a chat box in our Virtuosity website as well. You can reach out to our colleagues there too, and they will link you up with the relevant person. So that will be all from us today. Thank you very much for your time, ladies and gentlemen. Thank you for your support. Do spend a few minutes of your time. Would appreciate if you could spend a few minutes of your time in our survey question after this. Thank you very much. Have a good day. Goodbye.